Hello everyone, today I would like to talk about spherical coordinates, velocity and acceleration in spherical coordinates. Um, I am going to show the relation between Cartesian coordinate system and spherical coordinate system with system. This is one system. This is X. This is Y and this is Z, and I'm going to draw a vector position R. This is R and this is point P, and now from here we can choose the direction of spherical coordinates. In this direction is R direction. In this direction is R. In this one is phi roof and theta roof. So R theta roof. Also, I'm going to introduce the angles. So this is the projection of point P in a XY plane, and this angle is phi, this here, and this one here is theta. This one here is theta. But what are the relation between polar coordinates and spherical coordinates and Cartesian coordinates? So we have to find those things. First of all, I'm going to introduce this angle, this triangle here, OP P prime. This is OP, so this is OP P prime. This one is Z, this one is R, and this one is rho also. And this angle, we can call it theta, is the same as this one. But in XY plane, we have X and Y here, and we have point P prime. This angle is phi or phi, and this is the rho. And we can zoom this triangle, which is, so this is phi, this is rho, this is X and Y. So sine of phi is equal to Y over rho, and only Y is rho times sine of phi. Cosine of phi is equal to X over rho. Only X is equal to rho times cosine of phi. From this triangle here we can find the rho. So we have sine of theta is rho over R. So only rho is equal to r times sine theta. And from here we can substitute the rho here, which is r sine theta sine phi, and for x we have r sine theta and times cosine phi. And from this, also from this triangle, we can find the z component. The cosine of theta is equal to z over r. The only z is r cosine theta. So this is the relationship between Cartesian coordinates x, y, and z to x, y, and z to r theta phi. So we can write x is equal to r sine theta cosine phi, y is r sine theta sine phi, and z is equal to r cosine theta. This is the relation between Cartesian coordinates and spherical coordinate system. From those three equations, we can find that r is equal to square root of x squared plus y squared plus z squared, and theta is equal to r cosine of x squared plus y squared plus z squared, and only phi is equal to arctangent of y over x. So this is the relation between x, y, and z to r theta phi. So if you know x, y, and z, you can find r, you can find theta, and you can find phi, and you can substitute in those equations. But if we want to find the velocity or the acceleration of a particle in spherical coordinates, it's a little bit more difficult, but we are going through it. I'm going also in this picture. So in this one here, we have to introduce the unit vectors r roof, this one, theta roof, and phi roof. The definition of unit vector is r roof is r vector divided the absolute value of this one. So this one is x roof plus y roof plus z roof divided by r. But x, y, and z we have x which is equal to r sine theta cosine phi, epsilon is sine theta sine phi, and we can find that x roof is r sine theta cosine phi plus y roof is equal to r sine theta sine phi plus z roof, which is equal to r cosine theta. All of this one divided by r divided by r divided by r. Unit vector in r direction is this R with this R, this one with this one, and for unit vector we have in x direction sine theta cosine phi plus in y direction sine theta sine phi, and in z direction we have cosine theta. So this is in r direction. The unit vector in phi direction, is equal to z roof cross r roof over sine of theta. So what is z roof cross r? This is the vector product. So this one is z roof cross r roof, which is equal to, I'm going to write it in matrices form: x roof, y roof, z roof, 0, 0, 1. The components of z are 0 in x direction, y in 0 in y direction, and 1 in own direction. And the component of r are sine theta cosine phi, sine theta sine phi, and cosine theta. So this is sine theta cosine phi, sine theta sine phi, and cosine theta. And you have to solve this matrix, which is I think it's not too complicated, and the result is minus sine theta sine phi in x direction plus sine theta cosine phi in y direction. So for phi we have, in x direction we have minus sine theta sine phi divided by sine of theta. Plus in y direction we have sine theta cosine phi divided by sine of theta. So the phi direction is in x direction is minus sine theta, so sine theta plus y in y direction cosine of phi. So I am putting in box because we need this one. We need this one and the unit vector in phi direction. And in the end we have to find the unit vector in theta direction. From this picture here. We can see that the theta. So this is the unit vector in theta direction. In theta direction, there is the vector can be represented in this form: phi roof cross r roof. Why? Because we know that the cross product between two vectors gives us the third vector. So we are going to do the cross product between phi roof and r roof, and this cross product gives us the third product, which is the normal in those two. So we can find this vector quite easily. Also, this one can be written in matrix form. So x roof, y roof, z roof, minus sine theta cosine phi 0 sine theta cosine phi sine theta sine phi, and the third one is cosine of theta. And this the result is in x direction. We have cosine theta cosine phi, cosine theta cosine phi, plus in y direction we have sine theta cosine sine phi cosine theta, plus in minus in z direction we have cosine of theta minus cosine theta. Maybe I should write this in down here because I need it. X roof is cosine theta cosine phi, plus y in y direction sine phi cosine theta, minus in z direction only cosine of theta. And this is the unit vector in theta direction. I'm going to end this video now, because in next video maybe it takes a little bit long, and we are going to find the partial derivatives of those unit vectors, because we need when we compute the velocity and the acceleration in spherical coordinates. See you next video. Thank you.